Lesson 2.7, we're going to look at linear equations, y equals mx. And we have talked about already in this chapter an equation y equals kx, where k was called our constant of proportionality. In this lesson, something that works for any line is y equals mx. We'll talk about a variation of that later on, y equals mx plus b. But for right now, with y equals mx, m is representing the slope. And, the question might be, well, why don't we use s for slope? Just remember there's other languages where different words may look different than our word for slope. So that's probably the reasoning for m being used rather than s. So if we look at this on page 129, a group of college students developed a solar-powered car and entered it in a race. The car travels at a constant speed of 100 meters per 4 seconds. So the first question, what representation can show the distance the car will travel over time? In other words, how could we show how far it's going over time? So a couple ways that we could show how far it's going over time. One would be that we could make a chart. Make a chart and say, this is this is our time and this is our distance. Okay. So for 4 seconds it went 100 meters. Okay, so then we could just keep adding, another 4 seconds, it's going to go another 100 meters and so on. Another way we could do that to show that would be to make a graph. When we're making a graph there, we could just stay in the first quadrant because we're not going to have a negative time or a negative distance. Everything's going to stay positive. And then part B, what expression can show the distance the car will travel over time? So what we could do is look at, it's 100 meters in 4 seconds. So if we divide that out, is 25 meters per second. So every second it's going 25 meters. So what we could do then to find the distance it's going to go, basically every second it's going 25 meters. So if let's say we let S represent the number of seconds that we're driving, so it's going 25 meters per second. So the expression we could use would be 25 times s. Think about, for example, in 4 seconds they gave us, okay, so in 4 seconds it went 25 meters a second. We could do 25 times 4, which would give us 100. Well, we already were given that, so that's not finding anything new, but it at least confirms that it probably works. 8 seconds, 25 times 8 seconds would be 200, and so on. Okay, the nice thing about an expression is then that can be used for any number of seconds. So we could give that expression and then people could substitute whatever numbers they wanted to find to see what the distance would be. Part C says compare the representation and the expression which shows the distance traveled over time more clearly. So in other words, if we had like a table or a graph, or if we have this 25s expression, which one's going to show more easily how far it's going over time? Probably we could say the graph or the table would be an easier way to tell. The expression, certainly we can use that easily enough to figure out numbers, how far it went, but just kind of to visually be able to see how far it went over time, probably the graph or the table would be showing those more clearly. So look at example 1. The students in Meg's class are building a fence around the class garden. How can they use the pricing for the different lengths of fencing to determine the cost for 50 feet of fencing? So if you look, they've given us some information here. We're trying to determine 50 feet of fencing. So kind of what they did, if you'll notice, these bottom two here, they've highlighted those as points on the graph. So 15, 75, 24, 120. They could have put the 630 on there as well. And this is a little bit of a difficult thing because these numbers are not exactly even. So it's probably a good idea when we're graphing these points to label what the numbers, especially like the 24, 120, because there's 125, there's 25, so that's not hitting on either one of those points exactly. So anyway, we've talked about before, I don't care for these upside down triangles that the book's doing because we want to find a change in y over change in x. If you'll notice on the graph, it does go through 0, 0, and it's a straight line, means it's proportional. So technically we could just divide the y by x for any point. So in other words, we could do like $75 divided by 15 feet, and that would give you $5 per foot. Okay, that would happen for any point that we picked. And if it's $5 a foot, we're trying to find for 50 feet, then we could just take $5 times 50 and figure out that that would be $250. What the book's doing is they are actually finding the slope of the line based off of their points. So for example, remember change in y over change in x, so maybe we could say we'll go up 45 and over 9 here. Okay, again backwards from what the book's doing. 45 divided by 9, which is 5. These other points, they went up 130, they went over 26. 130 divided by 26 also would be 5. And then again, once we know that it's $5 a foot, then we can use that like they've done over here in step 2. $5 a foot. We have this equation then. Okay, the book talks about here, they kind of slip this in subtly here. The slope is m, and it's y equals mx. Now they're using instead of y equals kx, but so y equals 5x would be our equation. Okay, because our unit rate, our rate of change is $5 per foot, and so 5x, if x is the number of feet, we can substitute 50 and then figure out that that would cost $250. So on the try it, they want us to write an equation to describe the relationship shown in the graph. If you look what they're having us do here, they're having us find the slope and they're having us write what the equation is. So that's kind of a preview for you. So we know in order to find the slope, we have to have 2 points on the line. One of the points on the line looks like it is at 480. There are several other points that we could pick here. If you look at the work that they've done in your book, the work they're going to have us fill in, you'll notice with our change in x, one of the numbers is a 3. So in order to fill in their boxes, we want to figure out when x is 3. So that would be the point 360. Now, like I said, technically, if they don't have these numbers filled out for us, we could use a different point. We'll talk about that more in a minute. So if these are my 2 points, I'm just going to come over here so we can see our points and our work at the same time. This you guys could be filling in off to the left here. Change in y, so our y values, we went from 60 to 80, so we went up 20, and we could again write that as 80 minus 60 to get 20. The change in x's, so we went up 20. Change in x's, we went from 3 to 4, so we went over 1. Okay, and again, if we're showing our work there, we could do that as 4 minus 3, which is 1. And then 20 divided by 1 is just 20. So our slope then is 20 over 1, which equals 20. Like I said, if you guys wanted to, you could, probably if I had a choice, I would just do the 0, 0 along with the 480 if you want, or 0, 0 and 120. That would be even easier, okay? Make it as easy on yourself as possible. 0, 0 and 120. I went up 20, I went over 1, and there's nothing more to it than that. So if my slope is 20, remember in this lesson we're talking about this equation y equals mx, and m is our slope. So all we're doing then, once we find our slope is 20, we're just replacing that in place of the m. So instead of y equals mx, y equals 20x would be our equation for this line. The convince me at the bottom says, how do the equations y equals mx and y equals kx compare? Basically, we have an m instead of a k, so that must mean that m is equal to k. And that is the case if we have a proportional relationship. Our slope and our k, our constant of proportionality, will always be the same if it's proportional. Example 2, a drone descends into a mining cave. The graph relates its distance below ground to time. Write an equation that describes the relationship. So just looking at this graph, this is going down, so this is going to be a negative slope. I forgot to show this, but one way to help remember negative slope, if you have this, and you can kind of make this into an n for a negative, and if we're creative, I guess this other one, we could draw a couple things there and make that into a p for positive. So that's kind of convenient. So anyway, to write the equation here, we need to pick some points. Again, if you want to keep things simple, 0, 0 happens to be there, so you can use that. I would probably use that in the 1, negative 250. The book is not using either of those points, but those would probably be the simplest. They're the smallest points we could use. And then just look at your change in y, change in x. So our y's, we went from 0 to negative 250. Means we went down 250. So basically 0 minus 250 is negative 250. And then our change in x, our x's, we went from 0 to 1. And so that's changing by 1. We're actually finding the change in y here, sorry. So probably what I would normally do actually is just take, well, we could take negative 250 minus 0, or you could do 0 minus negative 250. If we start with negative 250, we have to start with 1, and so 1 minus 0. So this would give us negative 250 over 1, which is negative 250. If you look at your units, This is meters per second is what we did. So negative 250 meters per second is how fast this drone is going. And then we can take that information to write our equation. So remember, it's just y equals mx, so we're just substituting our slope in place of the m. Substitute your slope in place of the m, which would be y equals negative 250x. And then we could use that to find out at any point how far down into this mining cave that the drone has gone.